All right. So we were going to introduce the concept of several variables. Now, to a large extent, the treatment of several variables is going to be similar to how we treated single variable functions. So previously, you sought to say that you can have a function f of x, and then this function f of x will just be an expression where you have a variable. The only variable here is going to be x, and we have 2x, maybe plus x squared or something. Now, in terms of multivariable functions, so here you're going to have a function that has two variables. It can be x and y. Sometimes you can have a function that has x, y, and z. You can have more variables. So here we're just looking at several variables. So to make it easy, we're going to move on from single variable functions to first two variables. And then after that, you should get how the connection goes from when we have one variable to when we have two variables. And then we're going to be touching every now and then, we're going to be doing maybe one or two examples where you also look at maybe three variables. But otherwise, if you're able to work it out in two variables, then extending the idea to three variables should not really be very complicated. Now, how do we treat multivariable functions? Well, the first thing that we want to start with is the domain and range for such functions. Well, you sought to say for single variable functions, the treatment of the domain and range was quite basic. For example, when defining the domain, if you have a function f of x and then a root is involved, you wanted to avoid having a negative under the root. Let's say you have a function g of x here. You wanted to make sure that g of x here was always greater than or equals to 0, because you know to say having a negative under the square root is going to give you complex solutions. Another thing that you wanted to avoid when trying to get the domain is if you have a function f of x, and this function is equals to maybe 1 over some function g of x, you knew to say that in this case, the domain will not have values of x that will make g of x to be equals to 0. You must never have this situation, because 1 over 0 is going to lead us into problems. So you really don't want to have that in your domain. So you wanted to avoid numbers that gave you negatives under the square root, and you also wanted to avoid numbers that gave you 0 in the denominator from your domain. And then once you avoid such numbers, then what remains from the set of real numbers will qualify to be in your domain. And then one other thing perhaps that you wanted to avoid when dealing with the domain for single variable functions is if you had a function f of x and then you have let's say a function g of x. Now the concept here for is that can never take negative arguments. In fact, can never even take an argument 0. So 0, if you tried it on your calculator, it will be undefined. So because of that, in your domain, you want to avoid values of x that will give the argument of the to be 0 or to be negative. So for such cases, the domain had to be values of x that ensure that g of x has to be greater, not even equal to, because here even 0 makes the to go into problems there. So you want g of x to just be greater than 0. So this is what you had for the domain, or to control your domain when you have involved. So for this, I'm saying you're avoiding negative numbers as the argument of the and also 0 as the argument of the Now, if you had the same function, but instead you have, let's say, and then they put the modulus of g of x here, what you now see here is that the modulus will sort out the problems of negatives, because the modulus will ensure that whenever g of x is giving us a negative solution, that negative will be turned into a positive solution. So here we see that we can never have that problem of having a negative as the argument of the but the modulus does not get rid of a possible 0. In other words, it's still possible for g of x to be 0 here. So in our domain, we will now only avoid values of x that give g of x to be 0. So in other words, the domain must never have values of x that will lead us into having g of x to be equals to 0. So here g of x must not be equals to 0. In the previous part, without the modulus, g of x was not allowed to be less than 0, and it was not allowed to even be equals to 0. G of x had to be greater than 0. But now we're saying less than 0 is fine because the modulus will sort out that problem. Greater than 0 is fine because we never had a problem with that. But equal to 0 remains a possible problem. So we just don't want to have it in the first place. Well, when we extend the ideas to several variables, we still want to avoid the same things. So if you now have a function of several variables, let's say x comma y, and this function now, we have a square root, but inside you have a function g, which is a function of x and y. So same as in single variable functions, we want to make sure that the argument of the square root, it must always be greater than or equals to 0, just like before. So you want to avoid values of x and y. Now, it's not just saying values of x. I'm saying values of x and y that will give the function g of x a solution less than 0. Because there we're going to have a negative solution under the square root, and we know that is going to be imaginary. So this is what is going to control our domain. And as you can imagine, if you have f of x comma y equals to a function 1 over g of x comma y, in just like in single variable functions, you want to avoid g of x comma y being equals to, you want to avoid this being equal to 0, because when it is equals to 0, you're going to have 1 over 0, which is what you don't want there. So that is what is going to control our domain. So you skip values of x and y that give you a 0 in the denominator, and then focus on the rest of what remains in the set of real numbers. And just as we saw in single variable functions, if you have f of x comma y being equals to line a function, let's say g of x comma y, just like in single variable functions, you also want to avoid the argument of the line there to be less than 0 or equals to 0. You want to ensure that the argument of the line is always greater than 0. So, of course, even when you have the modulus there, we're still saying that the only problem you have there is when g of x comma y is actually equals to 0, because the negative will be sorted out by the modulus, if that is what you have. Now, with that description in mind, let's look at a few examples to just make sure that you follow what I'm describing there. Okay. Consider this series of examples, and here we have a wide range of examples just to help you understand or put to practice the concepts I was describing earlier on. And when you look at these concepts, the first one there talks about a square root. We have the square root and the function under the square root, same as this, and this has a little bit of both there. You have the square root and the denominator, so you have to keep in mind what to avoid there. Then here is just the square root, and then here we have a line, but you mind that modulus and how I described it earlier on. And then here we only have a square root. So I am just going to demonstrate one of each type here, and ideally you should be able to work out the rest. So let's start with the first one. With the first example, what we have is f of x comma y is equal to x squared minus y squared. And then we see that in this case, our g of x comma y is x squared minus y squared. So remember what I said when you have a square root, you want to avoid having a negative under the square root. So you want to ensure that the argument of the square root must be greater than or equal to 0. What does that imply? It implies that x squared must be greater than or equal to y squared. So yeah, y squared there. So this is what we should ensure, or what we should have in this case. This is the condition for our domain. So x squared must be greater than y squared. Well, since we're looking for the domain and we have seen that the only condition that we have here is that x squared must be greater than or equal to y squared, how do we present our domain then in this case? Well, here we just have to include this part in our description. So how do you phrase it? How would you phrase it? So in terms of presentation here, there are a number of ways you can present your domain there. If you're going to go with words here, you can say that the domain is going to be a set of all points x comma y So it's going to be a set of all points x, comma, y, such that x squared is greater than or equal to y squared. So you can state it just like this. It's a set of all points x, comma, y that ensure that x squared is greater than y squared. You can write it like this. If you wanted to get rid of the square root there, you should not present it in this form. This would not be okay. You know, to say if you wanted to write x squared, if you had, let's say, the square root of x squared, something like this, this can only be expressed as the modulus of x. So the square root of x squared has to be expressed as the modulus of x. Why am I saying that? A good example I'll give you is if you had negative 2 here, or let me present it in 2 steps. If you had 2, or let me say 3, if you had 3 raised to the power 2 and then being square rooted, well, for this one, you might argue to say that 2 will answer with that square root so that you end up with just 3 as the solution. But what if you had negative 3 here being squared? Well, in this case, you have to see that the order of events here is that the negative 3 will be squared first to give you 9. So here you're going to have an in-between step where this first becomes 9, and when you square root, it comes to give you 3. Positive 3, not negative 3. So if you just went for that direct approach where you just cancel the square root with the 2, notice that in this case, your solution would have come out as negative 3. In other words, if you have the square root of x squared, this can be seen as just the modulus of x, meaning that if x is negative 3, the modulus of negative 3 will come out as positive 3. What am I saying there? It's a concept that we'll see later when we start looking at the definition of a limit later on. But what I'm trying to point out there is that by taking the square root this side and the square root this side, it's like we're going to end up with the modulus of x must be greater than the modulus of y. So basically, this is how it reduces. So if you're not comfortable with this approach of presenting them with the moduli, then you can just leave them as x squared must be greater than y squared. So you can do that. Okay, so we can present it in either one way or the other. Okay, so that's one thing. Now, another way that you can actually present this is by saying x and y are members of, in this case, because you're dealing with x squared and y squared. So you just wanted to show that this is also going to be the set of real numbers, but the real numbers square. So you're just scaling everything upwards by squaring them up. So x and y are members of real numbers, but x squared must be greater than or equals to y squared. So this is if you wanted to use set builder notation. So you'd have this condition in place, but everything else will be the same, exactly the same as how you'd present set builder notation in single variable functions. So you'd have x and y, and it's such that x and y are members of real numbers, but x squared must be greater than y squared there. So this is basically how you present them. Okay, so this becomes the domain here. We can do the same thing for this, but clearly this is just going to be similar to what we're just from presenting. But let's look at number 3 there, and how did it look like? Well, if you wanted to get the domain for not number 3, that's number 4, for f of x, comma y, in this case you have equals to, that's y squared, y minus x squared, and then this is over 1 minus x. So notice that here I'm just going for the domain. The range is going to be a whole different case. So let's first master the domain. If this is what we have now, how would you get the domain for this one? Well, here we see that you want to avoid the negative under the square root, and to avoid that, it implies that x minus, as in y minus x squared, has to be greater than or equals to 0. In this case, we see that y has to be greater than or equals to x squared. So this is going to ensure that what comes out from that square root is always greater than or equals to 0. But how about our denominator? We see that there we can also have a problem. That's a possible problem. Now, how do we sort it out? Well, as you remember from single variable functions, you want to ensure that that denominator it can never be equal to 0. So if the denominator cannot be equals to 0, what are we seeing there? It implies that minus x cannot be equals to -1, or x should not be allowed to be equals to 1. So we see that when x is 1, then it will imply that the denominator is going to end up being a 0. So how do we present this then? Well, here we can say that our domain is going to be a set of all points x and y such that these x and y must ensure that y is greater than or equals to x squared. So that is to satisfy the first condition. And the second part, x should not be equals to 1. So again, I'm saying the domain is a set of all points x, y, such that y is greater than or equals to x squared and x is not equal to 1. You can wrap it off, or you can spice it off by saying the domain is a set of all points x, y, members of real numbers squared. Why am I saying squared? Because that there has a square. Without the square, everything would be okay. And of course, if this maybe was to the power 3, then I'd say real numbers to the power 3. Okay, so basically this is how it is going to work when it comes to determining the domain for this one. Okay, so let's look at one more example. So of course, clearly you know how this one is going to play out, but let me just quickly run you through that one as well. Hold on. Okay, so what's that? Okay, so moving on to example 5. And for that example, we have f of x, y is equal to root 25. And then we have minus x squared. Then you have minus y squared. Again, we're just focusing on the domain of this function. We'll circle back to do the range later. Now, how do you sort out the domain for this one? It's similar to what we have looked at so far. Nothing new, but you see how this one will simplify. So just as you can imagine, we have a square root there. Because we have a square root, we want to ensure that the argument of the square root is greater than or equals to 0. But since this has to be greater than or equals to 0, what happens? Let's change everything. We write this, we get x squared minus y squared must be greater or equals to minus 25. Divide everything by -1, we get x squared plus y squared. But you know, when you divide or multiply by -1, the inequality symbol faces the other direction. So this is now less than or equal to positive 25. What does this imply? Well, here now it's telling us that the domain is going to be a set of all points x, y. Again, I'll say x and y here. These are members of real numbers. But because I see I am about to use x squared and y squared, so I'll say this is a set of real numbers squared. And then what else? What about x and y? Well, the only viable values of x and y are values which ensure that x squared plus y squared is less than or equal to 25. So these are the only viable values of x and y, values that ensure that that is what we have. Now, this is one way we can present it. But observe one thing. When you look at this expression, this can actually be identified. It's a conic section that you should be able to spot just by observation. And based on what you have on the left-hand side, you should see that this is a circle. And based on what you're seeing on the right-hand side, the radius of this circle is 5. So because of that, we can conclude that actually this statement that says that x and y, x squared plus y squared must be less than or equal to 25 It's just talking about a set of all points x and y inside a circle of radius 25. I hope you're saying that. Not radius 25, of radius 5. So in other words, I am saying that if this is what you have, and the radius of this circle is 5, then the domain is going to be a set of all points x, y that lie inside this circle and on the circle. So on and inside the circle of radius 5. Why am I saying on as well? Because we're seeing equal to or less than there. So this is why I'm saying that the domain is a set of all points x and y that lie inside a circle of radius 5. If you can't present it like that, then you can still just phrase it the mathematical way like that. Okay, so do you have any questions on that? Great. Okay, so it's the same concept that you'd use on the second one, not the second one, number 6. Where's number 6? Number 6 is this one here. But let me just break down that one so that I show you what we're going to end up with there in this case. Okay, so we have x, y is equals to root 36 minus 9x squared minus 4y squared. What are you going to have in this case? Well, it's a similar approach, but this one will simplify to give us a different conic section. Let's just look at it and appreciate how it simplifies. So again, we do have a square root. Want to ensure that the argument of the square root must be, just like before, it must be greater than or equals to 0. When you maneuver around, you will see that you're going to have 9x squared plus 4y squared has to be less than or equals to 36. By dividing everything by 36, this is going to reduce to x squared over 4 plus, this is going to be y squared over 9 is less than or equal to 1. Now try to look at this. Can you identify what this is? Can you see it? Look at it very closely. Can you identify it? An ellipse. Nice. That is an ellipse, yes. Now that you know it is an ellipse, how can you present the domain in words? How would you phrase it? What would you say for your domain here? Yeah. Need help? Okay, so in this case, this, yes, is an ellipse as you pointed out, but when we had a circle, it's taking time. Okay, so it's taking time to type. Okay, so, okay, that's okay. So I hope you do get how it goes. But in this case, when you had a circle, it was a set of all points x, y inside and on the circle. This is saying less than or equals to 1. So here would phrase it that it's a set of all points inside and on the ellipse or on an ellipse. And you can specify the ellipse by giving its equation. You can either say it like that, or you can say it's a set of all points, and then you can just say x, y, members of real numbers squared, and then you have, they must be controlled by this x squared over 4 plus y squared over 9 this must be less than or equal to 1. So this is going to qualify also as the domain. Okay, so I hope you were able to get that. And with that in mind, or with that done, let's look at that one which comes with the natural log ln. So in the seventh question, we have f of x comma y is equals to ln. Then you have ln, the modulus there, 36 minus 4x squared plus 9y squared. Okay, so what are we doing here? So in this case, we notice that we have the modulus there, we have a ln. And what do we avoid when we're dealing with the ln? I did point it out earlier. When you have a ln, you want to avoid what? You need to avoid two things. Yes, negatives, but not only negatives, and a zero. Nice one. So when you have a ln, you want to avoid negatives and a zero as the argument. But in this case, we have the modulus. So having the modulus dealing or sorting out that argument, what do we have to avoid in this case? A zero. So in this case, because we want to avoid a zero, we'll get the argument of the ln and say whatever this argument is, it must just not be equals to 0. It must not be equals to 0. So if this must not be equal to 0, what do we have? We now have 9y squared minus 4x squared must not be equal to negative 36. But I don't like the negative being there. So let me rephrase this by multiplying everything by negative 1 and rewriting it. So I start with 4x. This will be minus 9y squared. This must not be equals to 36. I didn't just multiply by negative 1 because I didn't like the minus 36 there. I am doing this specifically because I have a plan in mind. I have an idea of where this must go. Because already at this stage, I have identified the conic section we're dealing with. Can you see it at this stage already? Can you see the conic section here? Hyperbola, nice. You see, once I saw this part, that one term was negative, the other term was positive, I knew it was a hyperbola. Even when I moved the other term the other side, the right-hand side was negative. I need to say, I just have to make sure the right-hand side positive so that when I divide by 36, I'll remain with a 1 on the right-hand side. This would be x, why on earth did I write x to the power 4? This is x to the power 2 then. So this is going to be x to the power, this is x to the power 2, and this is over 9, then minus, this would be y to the power 2 over 4. This must not be equals to 1. And as you pointed out, this is indeed a hyperbola. So this is a hyperbola. Now, how do we present our domain? Well, this is going to be a set of all points x comma y such that then present it like this. Or you can say that it's going to be a set of all points x and y, but these points just must not be equals to, they must not lie on the parabola. So they must not lie on that parabola. So, but if you cannot do that, the best you can do is just say x comma y. These are members of real numbers squared again, but x squared over 9 minus y squared over 4 must not be equal to 1. That can also be, that's a good way of presenting your domain. Okay, now that we have exhausted how you sort out the domain, the next part would be to look at how you deal with the range.